Today I want to look at this idea of energy, which is what this whole unit's going to be about. And to begin with, let's look at the two major kinds of energy. We can have kinetic energy and we can have potential energy. And then there's some more specific kinds of energy, but these are the two big general kinds. So kinetic energy first. And I will be abbreviating this with KE throughout this whole unit. Kinetic energy is defined as the energy of motion. An object in motion has to have energy, otherwise it wouldn't be in motion. And if you take physics or a more advanced chemistry class, you would find that you can actually measure the amount of energy in something if you know how fast it's going and you know how much mass it has. And there's a formula for that. And we won't be doing that this year, but the faster it's going, the more energy it has. And we call that kind of energy kinetic energy. Now, the other kind of energy is potential energy, which is a little bit trickier to understand. And potential energy can be thought of in two ways. Sometimes we talk about it as stored energy, and sometimes we talk about it as the energy of position. Usually when we're thinking of stored energy, we're thinking of chemical energy. We're thinking of molecules that if you break them down, they will release energy in some other form, like maybe heat. So think of gasoline. We have this big can of gasoline, and it has a lot of stored chemical energy in it. And it's just sitting there, so it doesn't really have any kinetic energy right now, but it has potential energy. And then you set it on fire, and it explodes, and it releases tons of heat and tons of light. So that's why we say it has potential energy, because there's energy like stored in the molecules, in a sense, that can be released if the right thing happens, or the wrong thing happens sometimes. Now, the energy of position can be thought about in two different ways. One is gravitational potential energy. So let's say I take my pen and I hold it above the surface of the earth. So it has a certain amount of gravitational potential energy because it's going to fall to the earth if I let go of it. There's a force on it. The force of gravity wants to pull it, and I'm preventing that from happening. So right now it has a lot of potential energy. If I hold it higher up, it has even more energy. And there's a formula for this too. The mass times the force of gravity times the distance that you're holding it above the earth. Again, we won't be doing those calculations, but I just want you to understand that the higher you hold your object above the surface of the earth, the more potential gravitational energy it has. Now think about what happens when you drop it. You have this object up here, you drop it and it falls to the earth. It falls faster and faster and faster. So as it gets close to the floor, it doesn't have very much gravitational potential energy anymore, but it has a lot of kinetic energy because now it's moving. So I'm getting ahead of myself, but that's an example of how potential energy can be converted into kinetic energy. And that explosion that I talked about with the gasoline, that's the potential energy being converted into other forms of energy. So that's the two major categories of energy. And now I want to look at some more specific categories. And there are 6 of them. And one is electromagnetic. One is electric. And one is thermal. And mechanical. And nuclear, and what am I missing? Chemical. missed that one. We're taking chemistry here. All right, so that's the 6 forms of energy. So each one of those, let's talk about individually. Electromagnetic, you might not know this, but you're very familiar with electromagnetic energy because one kind of electromagnetic energy is light. So electromagnetic energy is always a wave. So we have an electric field and we have a magnetic field that both travel as waves. Now, it's kind of hard to draw the other one because it should be perpendicular to the board. So I'm going to draw it kind of like this. And you have to imagine really well that one of these is in the plane of the board and the other one comes out like this. So these two waves, the electric wave and the electric field and the magnetic field, are traveling together perpendicular to each other, and they have a lot of energy. Now, the smaller I make the waves, the more energy they have. And we'll be getting back to that later this year. But the type of electromagnetic energy just depends on how far apart these waves are. So for example, I could make one that has smaller waves, or I can make one that has bigger waves. And those will all represent different kinds of electromagnetic energy. So you're familiar with X-rays. Some of you probably more familiar than you want to be. X-rays is a kind of electromagnetic energy that has a lot of energy, and that's why it can be dangerous for us. Ultraviolet light that causes sunburns, that's a form of electromagnetic energy. Visible light is a form of electromagnetic energy that now has less energy than those other two that I just talked about, so it's not harmful to us. Infrared light, you've probably heard of that because there are infrared cameras. Infrared is often associated with heat. Gamma rays, you've probably heard about those. Those are very high energy, very dangerous rays, but exactly the same kind of energy, just more energetic. Radio waves, you've heard of those, of course. And those are very, very low energy. Those are around us all the time. So thankfully they're low energy and not harmful. So that's one kind of energy. Electric energy, we're all pretty familiar with that. We've got that in our circuits. So they will actually be, used to turn on the lights, for example, or run the stove or the dryer or whatever. Thermal energy is just another word for heat. So when we say thermal, that's the scientific word, but we really just mean heat. Mechanical energy means that we've got something with moving parts. So think of a fan, think of a propeller, think of an egg beater, think of your own self moving around. So anything that's got moving parts, that's mechanical energy. Nuclear energy, there's really two good examples of this. One is radioactivity. So down in the center of the earth, we have radioactive elements that are constantly, putting out heat, really, because it starts out as nuclear energy, which is then converted into heat energy, and I'm getting ahead of myself again, talking about conversions. Another form of nuclear energy is something that happens inside the sun. We have nuclear fusion going on, where hydrogen nuclei are fusing together to make helium nuclei, and that releases lots of energy when that happens. And then chemical energy. So I talked a little bit about that when I was talking about gasoline, but most any kind of chemical, and everything is made of chemicals, has some amount of energy in it. Now, one of the things that we need to get up front, right to begin with, is anything that is matter is made of molecules, more specifically made of atoms. And those atoms are always moving. So there's always some kind of kinetic energy associated with anything that's matter just because the molecules are moving. So for the next few days, when we talk about kinetic energy, though, I'm going to be thinking about the kinetic energy of the object as a whole. Is the object as a whole moving relative to the Earth? So we would say right now that this pen does not have kinetic energy. And we would say right now it does have kinetic energy. Now, the molecules that make it up always have kinetic energy because they're always moving. Since this is a solid, they're just like vibrating in place. But they're still moving, so they do have some kinetic energy. I think that's all I wanted to say about that for now. So let's talk a little bit about transitions from one form of energy to another, because that can happen. We have this thing called the law of conservation of energy. And the law of conservation of energy says that energy cannot be created or destroyed in any physical or chemical process. Energy can move around. For example, heat energy, that's the easiest thing to see. I have something that's hot and it cools off. The heat energy did not just get destroyed. The heat energy went somewhere. It went out of the object and into the air, or maybe into another object that was touching it. But it didn't get destroyed. Energy can be transformed into a different form also, and we have all kinds of examples of that. So let's look at this and say electromagnetic energy, for example. Let's go back to that can of gasoline that was going to explode. There is originally no electromagnetic energy in there. We have all stored chemical energy. And then we throw a match onto it and it explodes. And what you get out of that? Well, you get light for one thing, right? Flame produces light, and light is a form of electromagnetic energy. You also get lots of heat. You also get lots of thermal energy. So if the gasoline completely reacts, then you're not going to have any gasoline left. You're going to have carbon dioxide and water. That's what you end up getting, because the matter doesn't get destroyed either. But all that stored chemical energy, most of it became light and heat. There's a little bit of it left in the carbon dioxide and water, but as you know, carbon dioxide and water don't have nearly the amount of stored chemical energy that gasoline has. Let's see, let's think of, oh, here's a good transition, electric and mechanical, all kinds of examples of that. Anything you have that you plug it in and it therefore makes something move. So a fan, for example, an electric mixer, for example. What else would you plug in and make something move? Well, anyway, those are good examples of a conversion from electric to mechanical. So you start with electric energy and that makes something move. Now you can also start with electric energy and make something get hot. So think of your stove or your toaster. So electric energy gets converted into thermal energy. If you start with a battery, then you have chemical energy that gets converted into electric energy, because that's the whole point of a battery. And then that electric energy may be used to produce, let's say you have a flashlight with batteries in it, that might be used to produce electromagnetic energy. And if the light bulb gets hot, it also produces some thermal energy. So we have all these energy transitions that can happen, but energy is neither created nor destroyed, except right here. This is kind of special, because over here we have this caveat: energy cannot be created or destroyed in any physical or chemical process. It can be created or destroyed in a nuclear process. So we won't talk a whole lot about that this year, but you might be familiar with E equals mc squared. And probably when I write that down, you think, Einstein. Yes, Einstein made that equation. And what he said was, if mass gets destroyed, and that only happens in a nuclear reaction, it creates some energy. The amount of energy that is created when a little bit of mass gets destroyed is equal to that amount of mass times the speed of light squared. The speed of light, in case you don't know, is a very large number. And then you're going to square it and make it a really, really big number and multiply it times the mass, and that gives the amount of energy that is created in a nuclear reaction. So if a tiny bit of energy gets destroyed, if a tiny bit of matter gets destroyed and becomes energy, you get a lot of energy, and that's why nuclear reactions are so very powerful. But that's it today for energy.